All right, I think I'm ready. Okay, so let's go ahead and start. Sorry, I run a little bit late today, but so just as reminders, we are working on Unit 10 here. It's a little bit of a kind of a just some miscellaneous things. I wanted to at least ask people to take a look at some other machine learning methods that so just get a little taste of using KNN and naive Bayes this week. So I don't know, I might not spend too much time on these. I thought I'd do maybe talk about K nearest neighbors today, and we'll do the naive Bayes on Thursday. So both of these are the way, but both of these can be used for supervised learning. Both of these can be used for classification or regression, although naive Bayes doesn't really do regression that well. So we'll see, but they're quite a bit different in terms of the the mechanics of how you build a model. So a lot of machine learning. I'll get into it. So, but yeah, today I'll go over the K and N. So also, I did switch these around, but I didn't really have the numbers switched around. So the notebook is probably still labeled 9 instead of 10. So just be aware of that. But we are working on 9 and 10. And we're mostly doing stuff on supervised on support vector machines this week. So I thought I'd bring up the assignment 4 just real quickly. I did kind of start talking a little bit about that last time. I'll be happy to go into if anybody wants some more details. Wants to ask some questions about things, about the tasks and stuff. So I hope that the so again, kind of looking at that, I broke it into what I called 2 different tasks, but task 1 is really or multiple parts, but I actually have 3 tasks. Task 2 is really kind of very simple. So task 1 is really meant to be kind of a warm-up. It is a straightforward fit of a linear support vector machine. So in task 1, you're supposed to go ahead and load the data. So there is this. We have the usual structure or workflow for this assignment. So there are methods inside of the source assignment tasks that you have to complete, basically. Including the first one is just to load the data, but then I do ask to do like 2 different fits of the support vector machine. Need to fix my my headers here in the assignment. So anyway, the main purpose of what I call task 1 was really just to explore a little bit how the parameter C affects the regularization, basically, when you're fitting a model. So we're just doing classification on this assignment with support vector machines, starting with the linear classifier. So I probably mentioned this last week. So you should basically find that by modifying C the way it's described here, that there's a bit of a point that's an outlier. So you should see a pretty big effect on this particular data set for part 1 when you modify C, where it'll try and linearly separate the data for one particular value C, but that might not be really a good decision boundary for this set of data here, since in one point in particular is kind of an outlier. So by modifying C, you should kind of get what probably would ultimately end up being a better sort of a fit on it. Task 2 is I should fix the headers for that, but is really just to implement a function to do the Gaussian kernel on yourself. So the notation can look a little bit scary, but it shouldn't be all that tough to translate that. In fact, this should be pretty similar to some of the examples in the lecture notebook. So there's already some examples of kind of how Gaussian kernel works. So in this one, you are supposed to parameterize this using the sigma parameter in order to get this right here. So if you look at the function for this, you're supposed to basically be passing in two vectors, and sigma is more like a metaparameter, which controls that width. We talked a little bit about how this Gaussian kernel works. So this should just be calculating the similarity, basically, the Gaussian similarity between two vectors. So those should be both the same size, just a vector of some in dimensions. I don't remember if I mentioned it in the description or not. It should be pretty easy to write a vectorized version of this. So, if it makes more sense, you can write a loop first of all. But you should try and vectorize it. Basically, to get the measurement here. Everybody, and at this point in the course, hopefully everybody knows what I mean by vectorized versus non-vectorized, having a loop in there. So this implies that you just need to loop over all of the in values of the two vectors, take the square difference of those, sum that up, divide by your sigma squared, and take the the exponential of that. That gives you your Gaussian measure of similarity, right? But you should be able to do basically that same thing. You could, for example, I think an easy thing to do is to use NumPy's linear algebra. There is a norm for calculating the norm in NumPy. So that's one way that you could just do that directly. Or just look up the definition of the norm and implement it yourself, basically. So. And then task 3, I don't know. I suspect. And again, let me know if anybody wants me to talk a little bit more about these. I might most people probably, I don't think, should find it too difficult. This assignment will probably be easier than the previous one for the most part. So in part 3, you do have to kind of explore using the kernels with support vector machine. So part 3 is basically about fitting a nonlinear model using a kernel with support vector machine, right? So we kind of walk you through doing it using scikit-learn and using a Gaussian kernel scikit-learn, and then just the main point of the last part of this is it's supposed to be demonstrating that what you really are using is that Gaussian kernel. So the Gaussian kernel that you create by hand, if you follow this correctly, and you do have to change between gamma and sigma. So in scikit-learn, like we talked a little bit about last week, the Gaussian kernel is parameterized in slightly different ways, and Dr. Ng talks about it. So this is one of those kinds of things where it's helpful to know kind of the details of how this works. And this is kind of just a historical thing, but some groups of people parameterize it one way, some groups parameterize another. That's why you get two slightly different ways of specifying how to control the width of that similarity for the Gaussian kernel. Anyway, if you implement your function correctly, you shouldn't have to really do much at the very end for like the the third part of the last task. I think you shouldn't have to do anything. It will basically be calling your Gaussian kernel that should be implemented in the assignment tasks, the task 2 part there. So, I do, we can talk about this as well. I do ask you in one or two places. In the first one, hopefully I did mention this last time, so just a reminder on that. You are asked to plot the decision boundary, both for the linear fit and in part 3 for when we're using a Gaussian kernel to get a nonlinear decision boundary. So for the linear one, I do ask you to do it by hand again. So you have to pull out the parameters of the support vector machine. We did a similar thing in a previous assignment. So pull out the parameters, use that to determine what the decision line was for the data that we had on task 1, and visualize that, plot that for our classification task. Right? So for the other part, task 3, where you have to do a nonlinear decision boundary, you're asked one or two places also to visualize the decision boundary. In that case, you will need to use like a contour plot, or at least that's the easiest way to plot the decision boundary. So there's a couple of examples of doing that in the lecture notebooks, so you should be able to use any of those examples to make a contour plot that correctly shows where the line is that ends up being the dividing line, the decision boundary between. This is a binary classification task in both of these, so we've only got yes, no for these. But you're not asked to do this, but if you want to, this would be a good example of you need to do that twice. You might want to use the function or modify the function shown in the lecture notebooks for plotting the decision boundary. But if you want to, you can instead of copying that code. So the general idea is you really should try to keep not have copies of code in lots of different places. So once you find that you're reusing the same function or the same cell in a notebook multiple times, it's a good idea to put that into a function and then reuse the function. So in this case, you should only have to use it twice, but wouldn't be a bad idea to go ahead and put that function as well into the assignment tasks and call it where needed, even though that wasn't asked for, so we didn't have a task to do that specifically. But you can do that in general for this assignment and other assignments like this if you're doing a bit of code that you reuse multiple places that you go and put in the assignment task. So, all right. And also, I'll keep reminding people about the class project as well. So I encourage you to do a little bit of work on that each week. So, since I was talking about reuse, that's another thing that I've discussed a little bit before. So one of the purposes of the source subdirectory you might have in your class assignment project is you might have multiple notebooks, but you might develop certain functions that you reuse across notebooks or multiple times within the same notebook. So if you find yourself doing that, again, follow best practices. Don't make copies of your code multiple places. Try and practice reuse, right? So, if you're doing the same thing multiple times, get that into a function, parameterize the function, and then reuse the function instead of copying and pasting lots of code different places, right? So that just makes your notebooks tougher to maintain. So if you want to make an improvement or a modification or a fix into a bit of code, and if you've copied and pasted it, you have to go through everywhere and fix that instead of having it in one place, one definitive implementation that you can improve or fix. So for example, if you create a function in order to capture your data cleaning step, like maybe a pipeline in order to take your initial data and generate a set of features that you're going to ultimately use in your project to build your models and things with. If you decide that you want to tweak that workflow or something, and if you have it in one place, it's easier to tweak it for everywhere that you're using it, as opposed to having like multiple copies of it. Okay, yeah. So I think that's enough for the assignment. So let me know. We can again. You've got this week for the assignment 4 that you should be working on. If you haven't started already, even though I think most people will find this a little bit easier than the previous assignment or 2, but you should still get started on it if you haven't done it yet. And make certain that you have everything done by Friday as usual for our assignment here. But yeah, we can still have some time if you want to email me questions or want to ask on like our next class session on Thursday as well, if you're having some issues with it. So, one other kind of quick note on this. I think that this assignment, especially task 3, can take a bit of time. So I don't know if people are going to run into issues with it timing out. So when you make a commit and push it back to GitHub, when it tries to rerun the whole notebook, there's like a time limit when it runs the auto grading tasks on GitHub using the GitHub Actions. So it's like 10 minutes is the default. So I don't know. People may run across that. So I'm just saying, maybe be aware of that. It could be the case that it looks like when it tries to run your notebook, see if it runs cleanly, all the cells run cleanly, that it's failing your task. It's failing that when it tries to do that, but it might be that it just ends up taking a little bit more than 10 minutes. So it fails because of timeout instead of your notebook not working. So in the one case, failing because of timing out is not really an issue. I mean, you might have everything right. We just need to up the time limit, or you might have to maybe think a little bit about. So a common reason why that might happen is when you do your contour plot, you might want to make your grid size not quite so dense, right? So you can control when you do a contour plot kind of how precise it is by specifying, like your grid size, right? So if you make that bigger, by the grid size I mean, like if you're dividing your x-axis, you could divide it up into a linear of 100 points. That might be too big, so 100 by 100 would mean that you have 10,000 points on your grid that you're calculating for the contour plot. That might take a lot of time. So if you reduce that down to like the 50 by 50, you're reducing it to only a quarter of the size, and that can increase. So just make it, just make your grid dense enough so that you can visualize it correctly, but it doesn't have to be too dense, so dense that you're spending minutes getting your contour plotted here when you visualize these. So that's one thing you can do to kind of reduce your time, is play around with that when you're visualizing these decision boundaries here. All right. Yeah. Any questions on that? Things about assignment 4? Okay. So let's move on. Close this off here. Let's go on to the Cadence neighbors. So. Check we're still running here. Okay. Like so. All right. Okay, so for the rest of today, I'm probably going to go over the, so again, this is labeled Unit 9. I kind of switched those, but I'm going to go over the K nearest neighbors, just talk a little bit about that. Both this one and the other one might not take me all that long to talk about them, but I did want to kind of introduce people to the basics of these. I'll also remind, again, if you haven't take advantage of looking at Dr. Ng's lectures on the support vector machines, I would really recommend kind of going through his treatment of support vector machines. So I think it's very useful. He gets into a lot more of kind of good explanation of some of the details of the mathematics of how these work. So I think it's very useful to kind of use his supplementary material on the support vector machine for the assignment and our unit this week and the previous week. So I don't have actually the K nearest neighbors and the Bayesian that we're looking at this week. This is kind of really supplemental material. Our textbook doesn't really have a presentation of these. There are a couple of links if you want to do a little bit of self-study. So most of this notebook here comes from the stuff. Hopefully I didn't get a chance to check if these are all still live links or not. Hopefully, yeah, so that one's dead, it looks like. I'll have to see if I can find the towards data science. Okay, well, sorry, need to update those. So it looks like only the first one is working right now. So probably if you Google that title, they probably just move the page, hopefully, on the towards data science one if you want to find those. I'll try and fix that and update those links. So, a lot of machine learning courses often start with K nearest neighbors. K nearest neighbors is very simple to understand how you actually train a model. Okay, it's quite a bit different from the linear logistic regression way that we mostly have concentrated on so far up to this point in the class. Right? So that's another reason why I kind of do like to throw these in here. This one, the Bayes and the ensemble learning use kind of quite a bit of fundamentally a different way of building a model, supervised learning, than what I think of as kind of the typical way that you see with logistic regression and support vector machines. Right? So it is. You shouldn't confuse K nearest neighbors with K means. Later on, when we get to unsupervised learning, we'll also talk about K means, which is a way of doing clustering, but they don't really have any relationship. KNN, K nearest neighbors, is a type of supervised machine learning algorithm. It's extremely easy to implement. In fact, I can't remember, but in this notebook there might be an example implementation, or if it's not in this notebook, it might be in an old one that I have. There's an example of just implementing it by hand in here. No, I'm wrong. It might be in an old notebook. Let me check something real quickly here. I'll have to look for that as well. I might have removed that, so I don't see it immediately here. Anyway, so let's just use what we have right now in our class resources. So relatively straightforward. It's easy to do implementation by hand, but there's an implementation in scikit-learn. Most machine learning libraries in Python and R will have nearest neighbors classifier. You can use KNN for regression as well. So both supervised learning kinds of tasks you can do for KNN. So yeah, it's a lazy learning algorithm. So it doesn't really have. So when we fit a model using logistic regression, we have to fit the model, right? So we have to go through some sort of an optimization task to find the set of theta parameters for a model like logistic regression. So for KNN, there's no equivalent of that. The data is just the data. There's no training. All of the calculation that you have to do happens when you do predictions with KNN. Okay? So and just to jump to kind of the conclusion on that, what KNN does is, what the name means is, if I want to classify a new unsigned point, I need to have some measure between how close. So I have some measure of similarity or closeness, right? And then for k nearest neighbors, so if I can measure how close a point I haven't seen is to the points I'm using to make predictions with, if k is 3, I might take the 3 nearest neighbors, the 3 most similar points to the one I'm trying to classify, and then use those points to make a prediction, right? So if all 3 of those points, so let's think of binary classification. So I'm probably jumping ahead here, but so here as an example, if we're doing binary classification, and if we have a real simple data set like this, where blue is, let's say blue is the no and the red is the yes here. One measure of closeness or similarity is we could just use Euclidean distance, right? So if I have a new point, x here, and I want to classify that, whether it's blue or red, whether it's no or yes for a binary classification task, I could set k as 3 to get the 3 nearest neighbors, where nearest here we can just define as the Euclidean distance. So you can visually see that these 3 are going to be the 3 nearest neighbors to that point if I'm trying to classify it, just by the Euclidean distance, the sum, the square root of the sum of the squares of the differences on each of our dimensions, right? So we're just 2-dimensional in this example here. So then for binary classification, we can do something pretty simple. We could just do like a majority vote. So if we're using an odd number of points, like k is 3, we're guaranteed that one or the other is going to have more. Right? So in this case, we had 2 reds or 2 yeses and only 1 no. So we would predict that this is going to be yes rather than a no, even k of 3 for k nearest neighbors. Right? And you can use a bigger k, so I could use the 5 closest neighbors, which would probably end up including that one and that one maybe. But we would still be voting for the red or the yes in that case, because it would be a 3-2. So you can do something. You can do more sophisticated things in order to figure out your decision. So we could do like a weighted vote. So we can take into account not only the 3 closest points, but how close they are. So we might give more weight to the closest points and less weight to the further ones, right? So just using like a weighted average where the weight is based on your distance or your similarity measure is a common thing that you can do. So if you use KNN, the default for like scikit-learn's KNN, I think is to use like more like a weighted kind of combination rather than just a straightforward majority. Straightforward majority, if you use an even number, k, so if you use k as 4, And if that happens to be the fourth point, then you can't end up with a tie. So you have to do something about how do you break a tie if you're just using a strict majority. So I don't know what the default is for scikit-learn to do that. But right. So for k is 4, if I have 2 no's and 2 yeses, I'd have to do something ultimately to say what my prediction would be for that point there. Anyway, back to implementing KNN. It's a very straightforward to implement. So like we said, it's lazy. There's really no training or no fitting that needs to be done. All of the computation happens when we do predictions, right? So to train a model for KNN, it just has to remember what the points are that we're going to use to make predictions with. And then predictions, and you can't do anything beforehand, right? So which are the 3 nearest points are going to depend on the distance for the point that I'm trying to make a prediction for, right? So any point that I select is going to have a different set of predictions. So I have to calculate the distances after the fact when I'm making my prediction, right? So if I want to predict, say, this point here to that one, I'm going to have to calculate the distance between that point and all the other points in my data set, right? And then sort them to find the 3 closest ones, or whatever n is, whatever k is that I'm going to be using for KNN. So we haven't really ever talked about this even for logistic regression, but this is kind of a drawback for logistic regression is that if I'm getting new data, if I want to incorporate new data, I have to retrain the whole model. I have to refit like a logistic regression, so redo the optimization. And depending on how number of features that you have and those kinds of things, it might take a long time to do that, right? So to keep your model up to date as new data is coming in. So KNN, there's no training. If I have new data, I just add that to the database, and it just has an impact on the back end then when I'm trying to make predictions. So yeah, there's really only one metaparameter that you can tune, which is the number of points that's not true. So the metaparameters, k is the most obvious one, so that'll have an effect, right? So if you use k as 1, you're just, this will have a similar function to like regularization that we've talked about, right? So the smaller k is, the more likely that you might be overfitting a bit. So if I happen to be closest to an outlier point, I'll be more likely, if I'm using just a very small k or just k of 1, I'll be making wrong predictions. But if I make it really big, you can go on, become too general then on the other extreme, right? So again, usually k is, there'll be one value of k, one or a couple, where it is optimal, where it gives you kind of the best performance in terms of accuracy or recall and precision. Okay. And in fact, scikit-learn, hopefully this is discussed in this notebook here, it will automatically do that for you. No, I'm wrong. For scikit-learn, you do have to specify k. So if you need to, you would have to do like a search over k to find out what a good value of is for it, for using for your data set. Yeah, another metaparameter. Well, there should be some others here as well. So you can do like the strict voting versus the weighted voting or weighted average I talked about. You can use other distance functions, so that's another thing you can do with scikit-learn. So I don't think I've discussed those. We'll mostly just stick with thinking of that as Euclidean distance, but there's different definitions of distance or similarity that you could potentially use as your measure, which may give you better or worse results depending on the data set that you're using. So KNN is usually not considered like a state-of-the-art classifier, so it's not going to work well with large data sets, especially things that have large number of features, like is mentioned here. So if it's high dimensional, later on later on in this course we'll talk a little bit about when we talk about unsupervised learning, some of these issues with high dimensional data. So KNN can for a classification algorithm, can be particularly sensitive to that. The basic reason is that the larger, somewhat kind of non-intuitively, the larger the number of dimensions, the more likely you are to be really far away from one or more features. So that has kind of that has implications about how well it will work. So, but KNN's often kind of a good basic one. Another one that can work well is kind of a baseline, right? So you might first try a KNN and as kind of a target to shoot for in order to improve upon, right? So using something better like support vector machine or something, you should be able to improve on KNN usually. Right? If you think of KNN as kind of a baseline performance a lot of times. So yeah, there's no computation needed to fit or train the data set, but once you fit a model like logistic regression, usually the computation to make predictions is very small. So it's kind of reversed for KNN. Here, especially with a large data set, you have to calculate the distance between each point you're trying to predict for and every point that you have in your data set, your database that you're using for the KNN. So that can take some computation to do that. Categorical features, for lots of different classifiers, categorical features can sometimes be difficult, so you have to handle them. We haven't talked maybe as much as we should have so far in this class about that, but because we mostly usually use numerical features. But if you have a category, you might have to encode it in different ways to get them to work well. KNN can be, at least according to some of these tutorials I had, can be problematic for KNN to have categorical features. This is just an example of using KNN a little bit with scikit-learn. So the API for using scikit-learn will be the same as what we've seen so far in this class. So here we're using the iris data set. We want to do classification. So this data set is pretty small. It only has 150 items in it. If you remember the iris one, it's got just 4 separate features that are all numerical. You have the sepal length and width and the petal length and width. So I'm kind of skipping over this. A lot of the stuff is stuff that we're somewhat familiar with in this class. So in this example here, we're doing a train test split because we're going to see how well our KNN is working with different values of K, I believe, here in this notebook if you look through it. We do some feature scaling, although for the Irish data set, the features aren't all that, they're pretty similar in scale, so this probably doesn't really help very much. Doesn't do very much here. So here, I did kind of, let me see here if I'm going to have to run the notebook here. Let me rerun the notebook. So here, we're doing the basic to create a classifier and fit. So it'll have all the methods that you're used to seeing in this class to perform classifications on a set of data. Rerun everything here. Mostly because I just wanted to kind of remind myself of the parameters. So you specify in using the in neighbors. This is the distance measure that's used, so it defaults to Minkowski, which is really just going to be, I'm sorry, no, the algorithm is the distance that's used. So So yeah, I don't want to get into it, but really the default when it's doing auto and it's when it's using the Minkowski with a P of 2, it's really that is Euclidean distance. So the default, I believe, it really is using Euclidean distance. If you work through all that, is kind of what it means. But you can use other things for that. So and I believe if I remember right, the weights allows you to specify whether it uses like a weighted or just a strict forward kind of voting. So uniform ends up being just like a strict vote where distance, weight, or weight points when we're making our final decision on which category. By how close, well, inversely to the distance. So the closer they are, the more weight they would have, right? So that allows you to do the kind of weighted voting like I was talking about. And the default for that is what is uniforms. Right? So it's just doing a strict forward, like straight up voting, the most number of wins. And also we didn't discuss, you do also have to, so if you're doing this will support multi-class classification, and that's what we're doing here, right? So there's actually 3 different classes. So I don't know exactly the details here, but again, so if I have 3 classes, if I use an N of 3, I could end up with a 3-way tie. So there is more stuff than kind of being described here that you'd have to worry about if you were actually implementing this by hand, how you would, the straightforward, so if I have 3 classes, and if I'm using uniform or just straight up, I can just count up the number that I have for each one of the classes, and if one of them is more than any of the others, of course it would be the winner, and that would be our prediction. But I could more likely end up having ties if I have a multi-class kind of a thing. So there, I suspect that probably if you end up with a tie for the uniform, it'll fall back to doing some weighting in order to try and break ties, most likely. So just to kind of finish up on this, so in this notebook here, there's only really an example of using it, kind of straightforward to do classification. So well, if we show kind of doing confusion matrix, computing the precision and recall for whatever parameters we fit here. So we fit it with a k of with an n of 5 and use all the other defaults on our training data. So yeah, if you're going to do a grid search, kind of an obvious thing would be to explore K here. So all we're doing here is doing ranges where the number of neighbors vary from 1 up to 40, using the Irish data set and showing what happens just on we're just using the actual accuracy here. All right, so we're just calculating how many we got wrong and averaging that. So this is really kind of a measure of accuracy here. So this is typical. So it might not be straightforward, but a lot of values give the minimum here. So if we use accuracy as our measure, definitely you want to do something below 20 or 21 because it starts having an effect. But small values of n of k here for the k nearest neighbor will do kind of the best. Probably, I mean, there's a little bit of fluctuation here. It's tough to say. But probably something in here is optimal, or maybe there. I don't know. Okay, anyway, we are kind of already mostly up for time. That was kind of really all we had in here. There's more we could say in here. I have to find, I know I must have removed it from our class resources. It is useful to look at kind of an implementation in Python of KNN. It's pretty easy to do. If you just have something that can calculate the distance between two different points, then you just have to calculate, if I want to make a prediction, I have to just calculate the distance between the new point and all my existing ones in the database, sort those, and then take the top ones, and then implement something to make your decision, like a straightforward vote. We're just doing that method. Right? So most people familiar with Python can actually implement KNN relatively easily, kind of by hand. So, for those interested, I'll try and fix those links there. So I'm sure that they probably just got moved. So, but probably if you just search for like building a K nearest neighbor. On here, hopefully it's still out there somewhere. So. Yeah, so I'll fix those in there. But if you're watching this, these are kind of good. So this one probably does show kind of by hand implementing KNN. This particular one here, maybe not. All right. Yeah, that's it for today. I'll let you guys go. So, we'll talk about Bayes on Thursday then. Give a final chance, see if anybody had any questions on the assignment for. But otherwise, just keep working on the assignment, and hopefully I'll see you guys on Thursday then. All right.